blast. You have to do it like this. Okay, great. Hi, Joe. Thanks for that. Right, we'll make a start. This is just a math catch-up session. Sorry for the delay. I think there's one of you is missing, but we'll make it slowly. First of all, sorry for the delay. YouTube has changed everything a little bit, and the problem is that that sometimes when you configure the software and everything, things don't go as planned. So when you go from a known session to a live session, it doesn't work too well. Right, I'll try to keep it to about an hour, so you can then kind of switch off. I know one of you is missing. Any ideas whether? Ah, yeah, there he is. I could just see it. 5. Okay, welcome to you all. Okay, so what we're going to do today is are we back on? I think we are back on again. Right, let's try and give it a go. Okay, all right, let me just check how we, yeah. I'm not sure, I've got a problem here with my system. It might be YouTube, it might be the software here. I may have to reboot. I'm going to see whether it's going to work or not. It might be YouTube. Okay, no, it seems to be working. Okay, right, let's carry just on. So anyway, let's go through this and then we'll see how far we go. So the first one we need to catch. Right, let me just, is mathematical terms. Yeah, so we need to look at a couple of questions. So the first one is, what is reciprocal? And one question we've got here is, what is a reciprocal? And it's not very hard to understand. The reciprocal is basically any number can be multiplied with another number, and the result is going to be 1. So we've got an example here. So the reciprocal of 8 would be 1/8. And so if you take 8 and you multiply it with 1/8, the answer is going to be 1. So it's fairly straightforward. The next one is, what would be the reciprocal of 15? And the answer is fairly straightforward. It would be 15 times 1/15, and the answer is 1. Yeah. And the same with the reciprocal of 1/3. So if you have got 1/3, all it is, you just turn the fraction over, and you get 1 as well. So 1/3 times 3 over 1, so to say, we would get 1 times 3 is 3, and then 3 times 1 is 3 as well. So 3 divided by 3, that's the result. That would be 1. Yeah. Okay, so it's fairly straightforward. Okay, let's have a look at the next one. And we've got a bunch of numbers here. And what I want you to do is just try to find the reciprocal of these numbers. Give it a go. See what you can come up with. If you want, you can put the answers in the box, in the speech box, or the chat box. Okay, I'll give you some time. Sorry again for the software packing up, but it's just the way it is with these things. Sometimes everything goes fairly smoothly, and you're just relying on third-party systems as well, so they sometimes work and sometimes they don't. Okay, yeah, spot on. So 0.5, yeah. If you put it in a fraction, it would be obviously 1/2. Yeah, yeah, Ryan, that's right. Next one, 19. What would it be for 19? 1/19. Yeah, straightforward. The next one, a bit more difficult. 1 divided by 7. Give it a go. See whether you can come up with. Yeah, spot on, yeah. So it would be 7/1. Yeah. So 7 times 1, 7 gives you, sorry, 7 times 1/7 gives you 1, yeah. The next one should be straightforward. So we've got 21 and 2069. What do you do with them to get the reciprocal? Right. Also have a look at 2 divided by 3, so it's not quite as straightforward. Yeah. How do you multiply it with another number to give you 1? Once you know the technique, it's straightforward. So 1/21, yeah, spot on. And then the same would be for 2679. Yeah, spot on. Yeah. Thanks, Ryan, for that. We've got few more people here. Feel free to join in the chat room. I understand if you're on the phone or so, it might be rather delicate to go and get into the chat room, but feel free to join in. Next one is 2/3. What is 2/3? What is the reciprocal of 2/3? 3/2. Yeah, spot on. Thanks, Ryan. So what you do is you just obviously you take the opposite. Yeah, if you've got a fraction, you just flip it over and multiply it with it. And it makes sense as well when you look at it. 2 divided by 3 times 3 divided by 2. So you multiply 2 by 3 in the numerator, so you get 5. And at the bottom you divide 3 by 2, you get also 5. Yeah, 5 divided by 5 is 1. Yeah, so you've got your 1. Okay, last one. We can spare the 21, but last one is the 25 divided by 2. What would you get for the reciprocal? It's a bit of a weird fraction because obviously you can get the fraction into real numbers. So what would you get? You would get 12.5, so 12.5 or 12 and 1/2, 1/2. So 25/2, what would be the reciprocal? Somebody, feel free to join in if you can. I think the other thing as well is you need to be registered on YouTube. If you are not, then it's difficult. So I do understand. Joel, thank you very much. 2/25, yeah, spot on, you got it. I'm gonna go to the next page. Right, need to get the next page. Alright, we've got these boxes here. Let me see if I can get rid of them. Delete, yeah, and delete. So we've got those numbers here. So you can see the results. It's just to reiterate, we've got 2. It would be 1/2 if you've got 2. 19, 1/19, 1/7, 1/7 would be 7/1, and that would be de facto 7. So if you multiply 1/7 by 7, you get 1. Then you've got 21 is 1/21, 2679 is 1/2679. And then we've got these difficult fractions. All we do is we just flip them around, 2/3. The reciprocal is 3/2, and when you multiply them would give us 1. Then we've got 21. The reciprocal is 1/21, and then 25/2 would be 2/25. So when you multiply the numerator and the denominator, you always get the same value. on top and above in the numerator and the denominator, and at that point you can just divide them, one by one, and you get one out. Okay, so having done that, we go to the next one. The next one is the definition. That's a definition which you need to know. Yeah? And it says here the reciprocal. The reciprocal is a number by which a given number must be multiplied to obtain a value of 1. Yeah? So that's the definition for this, and that's what you would need to know. Yeah? For the exam, so there's one question which comes up and they say define what a reciprocal is, and it gives you 1 point for that. By the way, the exam, just to mention this, there are 90 points to be had in the exam. You need 36 for a pass. Let me see, I've just got it here. I can give you the exact information. So it says, what have I done with it? What have I done with the paper? Here we go, got it. So you need passes 36, a merit is 45, and the distinction is 67 points. Yeah. So in total you can gain 90 points. So it's not too difficult to get a decent grade out of it. And so each question carries about how many points have we got here? I'm just looking at one. So I've got 6 points, 8 points in average for each question, some a bit more, some a bit less. Yeah. And some of them are fairly easy. And so far in the course we've covered the first question and a little bit of the second question as well. Yeah. So if you can do all the conversions and everything, you're already 1/3 to a pass. And the rest there's a lot of stuff which is fairly easy and fairly straightforward. Okay, so you need to know this definition. Let's move to the next one, and this is the next one. The base, okay? So you remember, when we talked about numbering system, we always called it, for example, 9/5 to the base of 16, yeah? Or which is hexadecimal. Or if you wanted to express it in denary, we could say 51 to the base of 10 in denary, yeah? So what else could we say? We've got binary as well. So if you've got like 1 0 or 1 1, could be 11 in denary, but we would have to say base 2, so we know it's binary. We've only got two digits. Okay, this is a definition for the base of. So the base is the basis of each place value column in a number system, or the number of the digit or digits and letter in a system of counting. So that is the official version for the definition for what a base is. I thought about it and I barely understand it myself. So when I look at this text, I think, what? Yeah. And basically, my point is, when you put a definition down and the definition makes sense, you get the points for this definition in the exam. So you don't have to remember this word by word or memorize it. So don't worry about this. Just write it in your own words. I put something down in my own words, and this is the second definition below. The base is a description of how many symbols are used to define a number system. I thought that's a lot easier. So, for example, denary uses 10 symbols from 0 to 9, and hexadecimal uses 16 symbols from 0 to F. Something like that in your own words, and you get the point for this question. Yeah. So should be fairly straightforward. You need to obviously explain these two expressions for the exam. So it's something that's necessary. Okay, how far are we? We're 21 minutes down. Okay, we've still got time. Okay, let's go to the next slide. This is a slide here. And this is the matrix prescale. Let me just get rid of the stuff that's underneath there. So and get rid of that one as well. It's a problem. I try to run it as a slideshow. If I do this, I've got two screens here. The second screen gets wiped out, and I need to look at the screen to find out whether the stream is still going. I've got all the software loaded on the second screen, so really I would need 3 screens to keep this going. But anyway, here we go. Okay, so some of the words you may recognize here. So for example, kilo, I'm sure you recognize. So you've got like a kilo of, what would you have a kilo? Sugar, maybe, half a kilo of sugar. when you go to the shop, and that's just a metric term. Mega, you probably recognize that as well, so it's megabytes on your computer. In the olden days, today we are talking about gigabytes, so when you look about storage and so on. Terabytes is the, obviously, when you buy a disk nowadays, an external disk, it's got like maybe 1 or 2 terabytes. And you've got like a rough idea, so those terms, they've crept in. And then on the other side, if you follow the mouse, we've got this 10 to the power of 0. Again, if I ask you what it is, it should be 1, should come straight away. So these are just the units. And then we've got this side here. So they're not minus values. They're just numbers between 1 and 0. Yeah? That's all they are, between 1 and 0. So we've got like a whole world of numbers between 1 and 0. So they're really, really small units. And we've got milli, micro, nano, and pico. Yeah, so they are the small units. Again, when you look on this side here, you've got a lowercase k, uppercase m, uppercase g, and an uppercase t as the symbol for the unit. And then here on this side, we've got a lowercase m, and this is sometimes confusing because lowercase m means milli, uppercase m means m, and sometimes the way people write, it's very hard to differentiate between an uppercase and a lowercase m in the unit. So when you make engineering drawings or you put some values down, it makes sense to emphasize that it's either a capital M or a lowercase m, so that you can differentiate between mega and milli. So a millivolt is much different to a megavolt. I mean, megavolt, do we use them? Doubt it. That would be a really high voltage. Maybe in a lightning strike you might get a megavolt. I think the highest we use is kilovolts, so thousands of volts, and then the lowest we use might possibly be microvolts. Yeah, when we look at electronics units. Okay, let's go through this unit here. So we've got 10 to the power of 3, that's a kilo. 10 to the power of 6, that's a mega. And 10 to the power of 9 is giga, 10 to the power of 12 is tera. One thing you should notice is that that the increment, with our exponential number here, is always in threes. Yeah, so we've got 3, 6, 9, 12. Yeah, and our engineering units they always divide it within those steps of 3 exponential numbers. When we go between sort of in the world between 1 and 0, we've got -3, -6, -9, and -12. Yeah. So this is milli, so that would be a thousandth, a millionth for micro. For nano, I don't know, is it a billionth or something, but very, very low value. And then we've got pico as well. Also notice the terms here, so you've got some weird letters. So that's a Greek letter called mu, and that letter stands for micro. And then nano, lowercase n, and pico, lowercase p as well. Okay, so this is one of the things you should sort of bear in mind. You will come across this all the time. So for example, when you pick up a multimeter, normally you get like a K or maybe a little m to indicate that whatever the reading is in millivolts. So instead of writing down on your meter 0.001 volts, which would be 1 millivolt, it would just be a 1. And then somewhere on the scale you would have a little m indicating that it's in millivolts. Yeah. So that's, again, is sometimes something you have to sort of bear in mind, and we're gonna look at. Okay, the next one. Yeah, it's a problem here. Okay, standard form. First one. So we've got express 578999 in standard form, and the answer would be 5.78999 times 10 to the power of 3. So this little sign here, because I can't, on my keyboard, I can't use a little 3 stuck next to the 10. We need some special software for that, but that little sign here just means to the power of 3. Okay, so you see this as well. So we've got 5,789, yeah, and here we've got 5.7, and then to the power of or times 10 to the power of 3. Yeah, and again, let me just, can I go in here? I can go in here. Let's try this. Here we go. So, for example, if I were to write this out, I'm just going to use 5.7. I'm just going to abbreviate this. Is times 10 times 10 and then times 10 and times 10. Or that would be equal to 5.7 times 1000. Yeah. So and that obviously would be equal to 7,000, 5,700, yeah, to sort of indicate this number. So why do we do this? Why do we use this 10 to the power of 3? Or when we use engineering terms, let me just go up. Why do we use the term kilo? Yeah, so we say 5.7 kilo, or for mega, 5.7 million or mega. And the answer is it's meant to make life a lot easier on us. So once you get used to these units, or to standard form, as it is described in the exam paper. So they will ask you a question of, put this number into standard form, and then this is what you're expected to do. It's just 5.7 times 10 to the power of 3, or to the power of 6, or to the power of 9, whatever it is. Again, the whole idea is just to make life a lot easier. So instead of having these huge numbers with 8, 9 digits, you've just got a single number, maybe a decimal point and 1 or 2 numbers after the decimal point, whatever is relevant, and then to times 10 to the power of 3, times 10 to the power of 6, or whatever it may be, is meant to make life a lot easier. In engineering, as I said before, we've got those engineering units, so we would use K, M, G, and so on. So, for example, when I go to Patrick to the stores, and I want some resistors, I wouldn't say, oh, I want some 150,000 ohm resistors. So I would just say, have you got some 150K resistors? Yeah? K standing for kilo ohms. And again, it's just meant to make life easier on us, or on engineers. And so we use this. Okay. Up to you. Try to put the following into standard form. Give it a go. I'll please, if you can, just go to the chat box and give me the results in the chat box. Again, that's an exam question which you will come across, to put something into standard form. So to give you a number, and you're meant to put it into standard form. So what you need to remember from this session is, what is standard form? Yeah, you just put it into a number and then times 10 to the power of whatever, and a little bit about engineering unit. But you're going to hit this later on in 308. Unit 308, quite a bit. Okay, guys, come on. Give me some numbers. Okay, for the first one, we've got -3. That's spot on, yeah. Thanks, Ryan. That's the second one, okay? So we've got 7 times 10 to the power of -3. Okay, spot on. What about the others? Give me some more numbers, and then I can go to the next slide with the answers. Also, feel free, if you struggle with any of the things I'm talking about here, just feel free to ask me, and then I'll go through it again. It's not a problem. Okay, we've got 6 times 10 to the power of minus 6, yeah, spot on. Spot on. What about some of the other numbers? We've got some of the positive numbers as well. Not positive, but numbers above 1. Now, always bear in mind when it says like to the power of minus something, it's not a negative number, it's just a number that is somewhere between 1 and 0. So it's a very small number. We've got 4 times 10 to the power of minus 6, to the power of 6, spot on. Yeah. 7.8 to the power of minus 3, spot on, thank you. Give me a few more numbers, 2 more, and then we'll move on to the answers. Okay. What's the time? Right. Okay. Let me move on to the next slide, and there we've got all the answers. Let me just get rid of this. Okay, so we've got 3989. Hi James. Great. Yeah, spot on. Spot on. Thank you for that. Thanks for joining in. Yeah. Okay, we got it. So what you can see here is we've got the answers here, and it's not that hard. It's just a technique you have to apply when it comes to it. When you go to engineering, you just have to get used to those units, to milli, micro, nano, and to me it's like second nature. But then again, I've been working in electronics for how long? How old am I? Far too old, but near enough 35, 40 years. Yeah. So it becomes second nature after some time when you deal with these units, engineering units, and and you just talk in those terms, and it's meaningful to you as well. The first time you come across it, it's actually quite hard to remember. So when you look at like the kilo, mega, gigatera, or at the lower end between 1 and 0, milli, micro, nano, pico. Yeah. But again, it becomes second nature after some time. Okay, I hope you could see the correct answers, if you got them. Let's move on and go to the next slide, and we are going into the world of electronics now. A little bit. So how much time have we got? We've got about 25 minutes. Again, this is just meant to be a little bit of a catch-up session of what we did yesterday. So we covered a lot more ground yesterday. But these are the most important things. The rest we're gonna, pick it back up again. Hopefully, I mean, I'm not sure whether you can be in next week, but if you can, we're gonna do this next week. If not, we'll do this later. Yeah. Okay. I don't need to get rid of the. Is it this box? Oh yeah, let me just try and get rid of this one so I can see this more clearly. This is the so-called magic triangle. That's what I call it, magic triangle. But it's Ohm's Law. Pretty much all that there is to it. To not all there is to it. There's a little bit more, a few more formulas to do, but you've got probably about 6 formulas, and they describe most of the stuff that's happening with Ohm's Law. So the whole idea about this triangle is whatever term you're looking for, you cover it up, and then you've got the formula. So for example, if I cover up voltage, it's going to be I times R. So I stands for ampere, for current, R for resistance, and V for voltage. And we've got the formula up here. So V is equal to I times R. So if I'm looking for I and I cover up I get the formula V over R. So I, or the current, symbol is I, the unit is ampere, it's a big A, capital A, is MV divided by resistance. Or if I'm looking for resistance, I cover resistance up and I've got V over I, and you've got the formula down here, so R is equal to V over I. So once you've got this triangle in your mind, so V is over I and R, then you can construct pretty much every formula very, very quickly. Again, when you start off in electronics, it's actually quite helpful. If you've obviously if you deal with this on a regular basis, it becomes second nature. Same as with those engineering units. Okay, let's have a look at Ohm's law on the next slide here, and is it coming up? I just need to get rid of this frame. Oops, got the wrong frame there. Can I undo it? Undo, delete. It's back there again. That's the frame I wanted to get rid. That's the frame I wanted to get rid of. Here we go. So this is Ohm's law. Yeah. So we've got a battery here, and I don't know whether you remember, I was talking about the photovoltaic pile. And when you look at sort of this old setup here, that sort of reminds one of the photovoltaic piles. So you've got your copper plate, a little bit of acid, a zinc plate, copper plate, a little bit of acid, zinc plate, and so on. And that's the same concept of a battery. So each cell provides about 2 or 3 volts. You stick them on top of one another, and you've got a permanent power supply or sustained power supply. So the little arrow represents a current, the bulb represents the resistance, and then the battery here, this sign here, represents the voltage. The voltage is the pressure. This is a diagram, I think you've seen it before, just to sort of illustrate what's happening. So a voltage will drive the current, and the resistance tries to restrict the current flow. And the resistance is normally, like a consumer unit. It could be a bulb, it could be a phone, yeah, it could be anything that represents a resistance. So it doesn't necessarily have to be a resistor. Okay, we've got a couple of circuits here. So there's one circuit here. Okay, let me just get rid of the thing there. Let me get rid of this box as well. It looks a bit more decent. What I want you to do is have a go and try and calculate what the current is, what I is. So the first step is you would have to try and work out the formula, and then I'm just going to go back to the formula to give you a chance to work it out from the magic triangle, and then you would have to just churn the figures through. Okay, I'm just going to go back to the formula. So here's the formula. Let you just write down what the correct formula is. Okay, I'm going to go back to the circuit, and what I want you to do is just give me some answers of what the current is in this circuit. Okay, spot on. Yeah. Let me just get a calculator up. Calc. Waiting for the calculator, and here it is. Yeah. So let's put it in standard form. Can put it to the side here. When we look at the formula, so the formula would clearly be V divided by R gives us I. So we've got 110 divided by 2,200, and we get 0.05. Yeah, spot on, Ryan and Joe. So it's fairly straightforward to sort of work it out by those formulas once you have got them. Let's go to the next circuit and give it a go. Again, just need to. Alright, let me try whether I can delete the stuff underneath. Yeah, we've done it, so we're okay. Give it a go. What's the voltage here? Okay, Ryan, thanks for that. Fairly straightforward, isn't it? It's just 5 times. So first of all, the voltage is V. And then when we look at the magic triangle, let's go back there for a moment. So we've got V. So we cover this up and we've got I times R. So we've got the formula here. V is equal to I times R. We're looking for the voltage here. So we've got 5 times 200. Yeah, we don't need a calculator for that. That's 1000. Yeah, spot on. Okay. Yeah. Thanks, Joe, for the attempt. It it's obviously it's just a formula. Getting the formula right is the key, and then you've cracked it. I'm just looking at how much time we've got. We've got about 15 minutes, and we might be able to crack a few more questions. Let me just go into my USB stick and get this up. Do we need this? I can put this in. Okay. So, by the way, this is George Ohm. He has designed Ohm's Law and came up with this in the early 1800s. Yeah. So he was sort of the second generation of the pioneers with sort of electrical and electronics systems. Yeah. He was just a school teacher in Germany. Okay, by the way, resistance, just units and symbols, we haven't covered this. So we've got A for ampere and the symbol is I. Yeah? So the unit is A. So that means when you write down, okay, we have got 1 ampere going through the circuit, you would write down 1 and then a big A at the end of it. If you represent a formula, you write down a formula. So for example, what is current? So I would be equal to V over R. Yeah? So you would use the I instead for the symbol. Resistance, so far you've just seen the symbol, which is R, but the unit is ohms. And that's a Greek letter. It's the last letter in the Greek alphabet, and I think it's a lowercase Greek letter. I'm not 100% sure, but I think it's a lowercase letter. So this one is called omega, and maybe because if you put an O there, it looks like a 0, so it's very easy to mistake this. Okay, we've got the 3 blocks analogy. We've got the water analogy as well when we look at Ohm's law. So you've got your water tower that generates the pressure. You've got the voltage, that would be the pressure. You've got a valve, that would be the resistance, and then you would have the output, the water that comes out. We looked at the formula. Okay, typical circuit here. So we've got the battery. Got the ammeter. The ammeter needs to be installed, needs to break into the circuit to get a measurement, and then we can get our current reading. And then the voltmeter, we always put it across our resistor to get a voltage reading. Okay, we did this. Let's do this one. Yeah. So we've got 2 amps and 30 ohms. What is a voltage? 26, yeah, Ryan, thanks for that. Spot on. Okay, again, V is equal to I times R, so 2 times 13 is 26, and you got it. Okay. Right. Move on to the next one. We've got 3 little circuits. I'm sure you can do it all in your without the use of a calculator in your head. How much time? We've got about 10 minutes left, so let's do this quickly and come up with some answers here. Thanks, James. Yeah, 26, spot on. Thanks for getting in there. There's a little bit of a delay. It's just something I need to make you aware of. So when I'm talking to you, and by the time you respond, there's probably about 10-15 seconds. So there's a tiny bit of a delay. Okay, we've got the first one. We have got V and ohms. Yeah. So that formula would be I is equal to V over R. 12 divided by 3 is 4. Thanks, James. Spot on. The next one. Thanks, Joe. Ryan. And Ryan as well, thank you, spot on. The next one, so we've got 9 volts, we've got 3 ampere. First, what would the formula be, and then what's the result? Yeah, spot on, 3. Yeah. So we've got 9. First of all, the formula for ohms would be, cover up ohms, and you get V over I. So 9 volt divided by 3 gives us 3 ohms. Yeah. The last one is supposed to be 0.5 amps. If you don't see the dot, you get slightly different results, but that's okay too, as long as the technique is right. So we've got 0.5 ampere and 12 ohms. So what's the voltage? Yeah, 6. So we've got 0.5 times 6 would be 6 volts. But obviously, if you didn't see the decimal dot in the slide, then it would be 5 times 12 and would be 60. So Ryan, you're spot on. James and Joe, you're spot on as well. It would be 60. There's a small decimal point. I don't know if you watch via the phone, you probably can't see it. I got these presentations. I don't know where I got them from, but they should have really stuck a 0 in front of it, if they wanted to make it a decimal point. But spot on, yeah. Okay, let's. How many minutes have we got? We've got about 10 minutes left. Let's do a few more. Yeah, we go to the next bit here. When we've got a resistor, you can see the resistor here. So there's a resistor there, there's a resistor there, and a resistor there. Yeah. And so this is called resistances in series. And there are, first of all, we need to know what is the total resistance if I want to calculate a circuit. And then the other thing is, what is the significance? There are two sort of important things there. First of all, the resistance just add up. Yeah, so that's straightforward. So if I've got a 100 ohm resistor here, and I've got a 100 ohm resistor there, and a 100 ohm resistor there, the total resistance would be 300 ohms. But there's also another aspect as well, and I want you to think about this. Yeah? So when you apply, for example, 12 volts here, and a current goes through those resistors, what you find is that the pressure of the electrons is going to be less after each resistor. Yeah. So if we stuck a meter across the first resistor, we would measure about 4 volts, 1/3, yeah, because that's 100 ohms, that's 100 ohms, that's 100 ohms. So it's going to be 1/3 of the voltage, which we're going to read over here. And then the next one, we're going to read another third, and then the last one, we read the last third. So we get about 4 volts here and 4 volts across there. And then whatever voltage we provide is going to be distributed across all those resistors. Okay. If you don't get this at the moment, don't worry too much about it. We're gonna revisit this later on. But that's something sort of to bear in mind with Ohm's law. And it's also important when you do sort of diagnostics in industry and you try to find out what's gone wrong or what's happening. So you can, based on that, make some judgments where you can see that, something is not right here, or winding of a motor has gone down or something like that. Okay, let's, how many minutes? I'm conscious of time. Let's move on. So we've got a circuit here, and based on what I just said, try and figure out what the current through the circuit is. Again, it's something you can do using mental arithmetic. You probably don't need a calculator for that. So what do you think? First of all, what is the total resistance? That's the first thing you need to calculate. And then the second thing is, what would be the current through the circuit? So what is RT and what is I? Okay, Ryan, you got 2. Yeah, let's That's I assume is for the current. Yeah, so it would be 2 ampere. And another thing as well, it's just sort of on a sideline. Whenever you do anything in electronics engineering, ideally you should write the units after every figure, so that people know, or somebody who's reading whatever you are calculating, that they would know what is meant. So it would be 2 ampere. I guess that's what you. Thanks, George, for coming in there. 2 ampere. Yeah. Again, when we calculate this, so we've got. Where's my mouse? I've lost my mouse. Here it is. We've got 4 plus 2, which gives us 6 ohms, and so then to get the formula would be V is equal, or I is equal to V over R. So 12 divided by 6 gives us 2 ampere. Yeah. I know there's an interesting thing as well. So when you look at R2 and you want to know how many volts will I find across this resistor. So I've got the current, which is 2 ampere, and the 2 ampere, they go all the way through. Yeah, so it doesn't change. So whatever comes out here goes back in here. Yeah. So we've got 2 ampere. So 2 times 4 is going to be 8. So if I put a meter across this resistor here, I would measure 8 volts. Yeah. And then I've got 2 times 2 is 4. Again, if I put a meter across this resistor here, I would get 4 volts. Yeah. So I've got 8 volts and 4 volts. And what you can tell me straight away is that, yeah, that's the same as 12 volts. So this voltage is going to get split up between those 2 resistors. And so you lose a little bit, not lose, but it's split up between those 2 resistors. Yeah. Again, just sort of bear this in the back of your mind, and so you can always do these calculations. Okay, 5 minutes to go. And this is another circuit. It's a little bit more difficult. So we've got 3 resistors in series. Can you tell me what the current is, and maybe what the voltage drop across each resistor is? Yeah. So give it a go. So first of all, you need to calculate RT. Then you have to calculate, so that's a total resistance. Then you have to calculate the current through the circuit, and this is probably something where you would need a calculator. And then once you know the current, you just multiply the current with each resistance, and you get a voltage drop across each resistor. Yeah, you get one there, you get one there, and then you get one down here as well. And all 3 voltage drops should be equal to about 45 volts. Okay, this is probably the last task for today, but after this we are almost there where I was with the other guys, yesterday. So give it a go. Right, total resistance, yeah, spot on. It's 22.5. Yeah, ideally put in a K. So 2 amps. Yeah, okay. Okay, here we go. So put in 22.5 K. Yeah. So that should be the unit, or kilo ohms. Yeah, because you can see a K as well. Really, we should put down. It's interesting as well that we do this for ampere and volts. We always stick by convention the unit behind. So we stick V or a big A behind it, capital A. But for resistances, we don't. And maybe because omega is not a letter you find on a keyboard, not sure. Okay, spot on, Ryan, you got it. Yeah. So let's quickly go through this all. So we've got 22.4 K. Let's get the calculator back up again. Okay. Whoops. So we get, let me just click on C. So we can just go through this. So we can stick as long as all of these resistors are in the kilo ohm spectrum. We can just use those numbers because we know it's in kilo ohms, and then whatever the result is going to be in kilo ohms as well. So we've got 5 plus 10 plus 7.5. And I mean, you don't need a calculator for this really, but anyway. So that's 22.5, and it will be 22.5 K. Then we've got 45 volts. Yeah. Okay. So 45 divided, and now you have to be careful because you came out with 2 ampere. Okay, let's see whether it works out. Yeah? So we've got 22.5K, so that would be the same as 22,500. Yeah? That would be the resistance in a normal number. Yeah? Not expressed in K, but in just a normal number. Okay, so when I put this in, I get not 2 ampere, but I get 2 milliamps. Yeah? It's very, very important. Yeah? It's a mistake you can make quite easily. So it's going to be 2 milliamps. Yeah? So when I were to type it in, it would be 2 and then a little m and a big A. Okay, are you with me on this? Because we are looking at kilo ohms, so if I divide a voltage by kilo ohms, the result would be a milli. But if I put the number in obviously in real terms, where I get rid of the kilo and I put in 22,500, then I end up with 0.002, which would be 2 milliamps. Okay, are you with me on this? I'm gonna stop at this point. Just want to check in with you that you're okay with everything we did today. Okay. Thanks as well for tuning in or coming in here on YouTube. Apologies again for the initial problems there. The YouTube interface has changed slightly, and that sort of gave me a few problems. Hopefully next time I can sort it out a little bit better. I thought I had it under control, but I didn't. But anyway, we came out the other end of the other side. Okay. Right. Any questions? Feel free to ask them now. And then once I end the stream, I think the chat room closes as well. Okay. Thanks, Jordan, for being honest. Okay. Also feel free to email me if you've got my email. I've emailed you with a link and everything. Feel free to email me if you've got problems somewhere, and I will try and help you via email. I'm not sure. Do you know whether you're going to be in next week or? Okay. Let's go back. I mean, we can do this. I'm just going to go back to standard form. So, guys, if you're okay with everything, then feel free to disconnect from the stream if you want to sort of get off or whatever. I said 3 o'clock will be the finish time, but I'll just go through standard form one more time. Okay. Right. Okay, when we look at standard form, it's again, when we look at standard form, we use numbers which are exponential numbers. Yeah, and when you look on here, we've got 10 to the power of 3, 6, 9, 12, and then here we've got numbers. So these are my units. So 10 to the power of 0 is my unit numbers. And then we've got 10 to the power of minus 3, 6, 9, and 12. So these numbers on that side here are numbers between 1 and 0. And on the other side here are numbers between 1 and infinity. Yeah? Could go as high as you would want it to go. In engineering, we just use steps of 3. And so we are looking with kilo, mega, giga, tera. And then between 1 and 0, we've got milli, micro, nano, pico. Yeah? It always goes in steps of 3. So whatever number you express, you just use any of these exponential numbers. Yeah. Okay. Let me just try and get Notepad up. Okay, that's not Notepad, Paint. Hope it's big enough. So, what is standard form all about? So we've got 10, the base of 10 with our exponential numbers. The exponential number sign you can use for that on a computer is that one here. And the whole idea is that when you put, for example, 10 to the power of 3, that would be equal to 10, to get used to this keyboard, 10 times 10 times 10, and that's equal to 1000. Yeah, 1000. So for example, if I had a number like 5678, and I wanted to just make it a bit easier to express, yeah, what I could do is I could maybe sum it up, just get it to the next biggest number, and I would decide, okay, the next biggest number is, let's say 5.6, yeah, 5.6k. So I could write down 5.6k. It's not really rounded up properly. Normally you should round up and go to 5.7, but anyway, not these, And then times 10 to the power of 3. Yeah, so that will be one form of expressing it. Yeah. So all I do is, what I'm saying is essentially the number I'm looking at is 5.6 times 1000. Yeah. And instead of using 1000, I just use 10 to the power of 3. That's pretty much all it is. What it comes down to. Okay. When I go the other way, so for example, if I've got we got a figure, before of 0.002 ampere. Yeah, that was a figure. If I wanted to express it in standard form, I could say it is 2 times 10, and then I use this sign here to the power of minus 3. Yeah, so I can't see the minus sign very well. Let me just separate this a bit. So that's 10 to the power of minus 3. That would be equivalent to 2 times 0.001, and that would be equivalent to 0.002 ampere. Yeah. So when that's just going from one way to the other. Yeah. So also you notice when you look at 5.6 times 1000, for example, you pretty much stick 5 zeros at the end, or 5 positions after the decimal point, and you've got the number. You've got 5,600. Yeah. The same also when you've got to the power of 6, you've got a million. So you would be dealing with 6 zeros. Yeah. And here also you get like 3 zeros, and then from the lowest position you start counting up, and same with the next unit down. You would have 6 positions, and then 9 positions, and 12 positions. Okay, let's give one more example. So the question you will get is something like this, yeah, in the exam. Put the following into standard form. That's a question, yeah. To be fair, I've never really come across the expression standard form, but that's my engineering background. We just use engineering numbers, yeah. And standard form is slightly different. So they give you a number, for example, like 6,987, 0.99, something like that, yeah. And so it's quite a big number, and they want you to put it into standard form. So all you need to do is you look at, what am I looking at? Okay, it's 1,000. 1,000 is 10 to the power of 3. Yeah, you can see this up here. So 1,000 is 10 to the power of 3. I just try to highlight this. Yeah. So we know, okay, that's 1,000. So that would be equal to 6.9. Let me try again. 987. And then 99. So we stick this over there as well. And then times 10 to the power of 3. Okay. So that would be the standard form expression, that one here. Okay, so that's basically what City and Guilds is saying, what you should be doing. I would be happy, because I think there are a lot of terms in this number which are not really that significant. Yeah? I'm not really interested in the 0.99 at the end of it. So if you gave me an answer like this, let me just put an equal sign there, and you just shorten it to just a few significant places after the decimal points, maybe 2 places or something. I would be happy with that. Or maybe it's easier to just use 3 places, because that's just the same number as before, but with 3 places. I would be perfectly happy with that, and I will give you the full points for this question. So times 10, and then to the power of 3. Okay. All right, George. Okay. Are you okay with this? No. Anybody got a question? Yeah. Okay. You're off next week as well. Good for Thank you for letting me know. So I know whatever I do with the class, I should sort of keep it aside, and then have the session for you as well, the same session ready. Okay. Anybody got any questions before I leave? If you are fine with this, then I'll end the session and wish you a good day. I hope if you got the virus, you're fighting it off mightily. Okay, good. Thanks, George. Anybody else still a question, or you want to cover something, you're not sure about something? Okay, no reply. It's always a problem with the delay, but it's just the way things are. So anyway, I wish you a great day. We'll meet up next week. I have to ask Gary when he wants to do this. Whether it's also on a Wednesday, and then also how much time. Okay, I'm just reading the text there. That's fine. So what we're going to do is maybe a morning, maybe an afternoon session, maybe both, depending on how much stuff we've got to cover. What we did this time around is we pooled 2 classes together, and we did just a lot of repetition. Yeah. So all the new stuff, I could condense it into 1 hour. So that's maybe next time we need a little bit more, maybe 2 1-hour sessions, or 2 1.5-hour sessions. I don't know. Okay, I wish you all the best, and I shall end the stream, and I will see you next week, or talk to you next week via YouTube. Have a great weekend, and all the best. All the best to you, especially if you are ill. Good, get well soon, and my best wishes to you. Okay, bye bye.